Hello once again, calculus students. Good to see you again. Today's topic is computing the derivatives of exponential and logarithmic functions. Logarithms and exponentials are further examples of transcendental functions like the trigonometric functions. Logarithmic and exponential functions have lots of application in engineering and science. You've no doubt heard of radioactive decay, and maybe you've seen population growth. These are the type of things that are modeled by exponential and logarithmic functions. Today we're going to develop the derivative rules for these kinds of functions, and also we're going to take advantage of properties of logarithms and exponentials to develop a whole new differentiation process called logarithmic differentiation. And this process can be used on a wide variety of functions, and it makes calculating derivatives a lot simpler in certain cases.
Hello once again. The topic for today is derivatives of logarithmic and exponential functions. Before we can start really talking about these derivatives, there's a little preliminary topic we need to talk about, which is the topic of inverse functions, which you've probably learned about previously in high school or maybe a pre-calculus class, but it would be worth taking a few minutes just to review some of that. So what do we mean when we say two functions are inverses of one another? In a nutshell, it means that the functions undo each other. If you have two functions that are inverses of one another, if you plug one into the other as in doing a composition, then they just undo each other. So the way that gets expressed is with these two equations here that I'm going to highlight in blue. See, those two equations mean the same thing when you're talking about two functions being inverses of one another. So when you look at the first blue equation there, it says if you plug x into f, you get back y as an output. And then the second equation in blue on the right is saying if you plug the output of the original one, y, into the inverse function, you get back the original input. So you can see this really just means that they're just doing the opposite of each other. They're undoing each other. And then you can see that's going on. Another way to say this very same thing is with these two equations I'm highlighting here in pink. The first one just says that when you plug f of x into f inverse, you just get back x. So that original x that you plugged into f on the inside, you get some output there, y, and then you feed that into f inverse and you get back x, which you started with. And the same thing happens when you do it in the reverse order there. So f of f inverse of y, you just get back y. So the functions are just sort of undoing each other. And it's worth pointing out here that first equation is telling you when you put x into f, you get back an output of y. So that means that the point x comma y is on the graph of f. And likewise over here, the second blue equation tells you that when you put y as an input into f inverse, you get an output of x. So that means the point y comma x is on the graph of the inverse. And when you combine these two things here, it tells you that the graphs of f and f inverse are related to each other in kind of a special way. They are reflections of each other across the line y equals x. Whenever you reflect points across the line y equals x, it just has the effect of switching the coordinates, right? That's kind of that's an interesting graphical way to think about inverses. The equation, the equivalence, the two things in blue, that equivalence is what we're going to be using the most today. But the one in pink is also kind of nice. It's nice to know that this is what inverse functions do. When you're solving equations, you use this sort of thing a lot to simplify things. Let's take a quick look at just a standard basic example. So we've got these two functions. F of x is x squared, and g of x is the square root of x. Now if I apply the thing in the equations in pink, I can see that these two functions are inverses of one another because it satisfies both of these two pink equations. So like for example, if I do f of g of x, that's f of square root of x, and the f function squares things, so you get square root of x squared, and that's just x. And here it's understood that x is greater than or equal to 0. Same thing if you do g of f of x, that's g of x squared, and then that means to take x squared and take the square root of it. And that actually equals absolute value of x, but again, we've assumed that x is greater than or equal to 0 here, so that just comes out to x. So when you plug one function into the other, they undo each other. And so that's what it means for the two functions to be inverses of one another. And if you look at their graphs, you'll see that they have this relationship of being reflections of one another across the line y equals x. I'll put that graph over here on the right now. So there are the graphs of x squared in red, square root of x in green, and then there's the line y equals x, and you can see that the red and the green graphs are reflections of one another across that line. And you can see, like for example, the point 2 comma 4 is on the parabola there, and then you see 4 comma 2 where you switch the coordinates are on the graph of the square root function. So just a little review of how things work with graphs of functions and their inverses there. Now, a few big facts that we want to remember about inverse functions is, the first is, how do you tell when a function actually has an inverse? Not all functions are invertible. So if a function is 1 to 1, which means that it passes the horizontal line test, then you know that that function has an inverse. Now, it doesn't tell you what the inverse is, it just says, an inverse exists for the function. So the horizontal line test just means if the graph of the function has the property that every horizontal line crosses that graph at most once, then you know that your function is 1 to 1. And if you know your function is 1 to 1 on a certain domain, then it's going to have an inverse. And then you'd like to know, well, what's the domain for the inverse function? So this is point number 2 here. The domain of the inverse function is just the range of your original function f. And then likewise, the range of your inverse function is just the domain of your original function. So if you understand your original function well in terms of what its domain is, that's just the allowable input values, and you know what its range is, that's just the output values that you get from the function. If you understand your function well like that, then you know all the good stuff that you need to know about your inverse function too. So in this bottom example here where we've got f of x equals x squared, we could take a look at the graph of x squared on 0 to infinity. Well, we already graphed it up here. It's the graph in red right there. Now, does that graph pass the horizontal line test? Do all horizontal lines only cross it at most once? Sure, just visually you can tell. So I know that f of x equals x squared is 1 to 1. And so then I know that f inverse exists. Now let's pretend for a moment we don't know that the inverse of x squared is the square root of x. How would we figure out what the inverse is? Well, there's an algebraic procedure for finding inverses that works as long as you can solve an equation, which you can't always, but sometimes this works. So the way it works is you got f of x equals whatever your original function is here. In this case, x squared. You replace f of x with y, and then you interchange x and y. So you change that equation into x equals y squared. Why are we interchanging x and y? Well, because we know that in the inverse, it does exactly that, right? The inverse exchanges x and y at every point for the original function. We saw that on the graph up there, right? And then you solve for y. And in this last equation, if I solve for y, I'm going to get y equals plus or minus the square root of x. But we assumed at the beginning that x was bigger than or equal to 0 because we said that we were talking about that function on 0 to infinity there, so that means x is bigger than or equal to 0. So you just end up with the positive root. I guess in ways it doesn't even really matter that x is greater than or equal to 0 because y is equal to x squared anyway, and we already know y is greater than or equal to 0. But in any event, we get y is the positive square root of x, and we can see that that's the inverse function then. So f inverse of x is the square root of x. The key step of this finding an inverse is being able to solve this equation after you exchange x and y. If you can solve that for y, then you can find your inverse. And then you can look at the inverse and you can see, so we've got f inverse equals square root of x, and you look at that function and see what its domain is. Its domain is all non-negative numbers, and its range is also all non-negative numbers. And that's what we were expecting to get because the domain of f inverse is supposed to be the range of the original function. And I can look up here at the red graph and see that the range of that function was 0 to infinity. Those are the y values on that graph. And I can also see that the range of my inverse function is 0 to infinity, which is actually the domain of the original function f. If you have some function and you want to start thinking about its inverse, you got to first make sure that you got a one-to-one function, pass the horizontal line test. And then you want to make sure you know what the domain of your function is and what the range of it is, because when you start turning it around backwards to get the inverse, the domain of your original function becomes the range of the inverse, and vice versa for the range. So let's see what we can do with this information. So the first big fact that we're going to take a lot of advantage of is that the exponential function e to the x and the logarithm function natural log of x are inverses of one another. This is one of your most famous pairs of inverse functions. So over here on the right, I have this blue graph, which is the graph of y equals e to the x. And I can tell by looking at it that it's 1 to 1. And so I know it has an inverse. Okay? And then for historical reasons, someone named this inverse of the exponential function logarithm, ln. All right. So then, based on our definition of inverses, we know that when you have two functions that are inverses of one another, by definition, f and f inverse, if they're inverses of one another, then you get these two blue equations are equivalent to one another. That's what that means. And so if we said y is equal to natural log of x, well then its inverse has to do the opposite of that. Its inverse has to take as input y and give output x. So that is equivalent to e to the y equals x, because the exponential function does exactly the opposite. So these two equations are equivalent to each other. Okay, now you might be thinking, I don't care. Why should I care that those two equations are equivalent to one another? That's going to be the centerpiece of how we get the derivative of the natural log function. See, we know that the derivative of e to the x is e to the x, right? That's just something we've already established. And I want to use that information that I know the derivative of e to the x is e to the x to find the derivative of natural log of x. So the idea is I can use those equations that are in blue, the fact that they're equivalent, I use that as a conversion factor to go from what I know about e to the x to what I know about natural log of x. So let me show you how that would work. So the idea is we're going to use implicit differentiation to find the derivative of the natural log. So this is our goal right now, is we want to find this derivative right here whenever x is greater than 0. So if I set y equal to natural log of x, what we're really wanting to do is we want to find dy dx, right? But this equation, y equals natural log of x, as we see in blue up there, is the same as the equation e to the y equals x. And then from there, I can take the derivative with respect to x of both sides. And the reason I want to differentiate this equation instead of the original one is because I know what the derivative of e to the y is already. Now on the left-hand side of that equation, the derivative of e to the y is e to the y, but remember, y isn't just a variable here, y is a whole function. In fact, we know that y is the natural log function. So I got to multiply times dy dx using the chain rule when I differentiate the left-hand side of that previous equation. And the derivative with respect to x of x is just 1. And now we can solve for dy dx, and we get dy dx is 1 over e to the y. Well, that looks a little weird, but if you just remember, what is another name for e to the y? Well, I'll give you a little hint. Look at this equation here that I'm circling. E to the y, another name for that is just x. So this just turns out to be dy dx equals 1 over x. So that's the derivative of your natural log function. So let me make it up here. The derivative of the natural log function equals 1 over x. So that's a pretty important formula right there. I'm going to put a box around it and highlight it, so you'll know it's important. Now, You can do a little extension of the derivative formula we just found in green that turns out to be important a little later, especially in the second calculus class. But we're going to go ahead and establish it now since we're here and we're doing this sort of thing right now. So if you look at the natural log of x, natural log of absolute value of x, that's a little bit of an extension of the original function, because the original natural log function, without the absolute values on the inside there, you can only put positive values of x into it. And the reason for that is the natural log is the inverse of the original exponential function, right? And when you look at the original exponential function, its range is 0 to infinity. So that means that the domain of the natural log function is 0 to infinity. And it looks kind of like this. Y equals natural log of x. So the original natural log function in red there, you can't plug negative values of x into it. And you also can't plug 0 in there either. You can only plug in positive values. But this function that we have at the bottom here sort of extends the natural log function that allows you to plug in negative values as well, because the absolute value gets rid of the negative for you. Anyway, if you consider x's that are positive first, you see that if you're taking the derivative of the natural log of absolute value of x, well, since we're assuming that x is greater than 0, the absolute values just go away, and you're just really differentiating natural log of x, which you already know that's 1 over x. On the other hand, if x is less than 0, if you take the derivative of the natural log of absolute value of x, well, whenever x is negative and you take the absolute value of it, you just negate it, right? So this becomes the derivative of natural log of negative x. Negative x is the absolute value of x whenever x is less than 0. And since we already know the derivative of natural log, whenever the input is positive, and the input is positive here because you're doing negative of a negative number, then I can use my previous derivative formula and say that this is 1 over negative x times the derivative of the inside function, which is negative 1. So I got to use the chain rule here. But then those negatives cancel and you get 1 over x. So notice that either way, didn't matter whether x was negative or positive, the derivative is 1 over x. So those two facts taken together tells you that the derivative of natural log of absolute value of x is equal to 1 over x just whenever x is not equal to 0. But like I said, we won't use that formula too much in the first calculus class, but it is important for the second one. All right, so all this is summarized in this theorem 3.15. Whether you differentiate natural log of x or natural log of absolute value of x, you get 1 over x either way. All right, so we could do some examples where we calculate derivatives now because we know how to differentiate natural log. So in that first example here, I've got y as natural log of x squared plus x. So if I want to do dy dx, well, we just learned that the derivative of natural log of something is 1 over that something. So this will be 1 over x squared plus x. But because there was an inside function here of x squared plus x, we have to use the chain rule and multiply times the derivative of the inside function, like that. And then when you take that derivative, you get 2x plus 1, right? So I can just write this as 2x plus 1, all divided by x squared plus x. So when you're differentiating natural log, you get to 1 over whatever's on the inside of the natural log, and then multiply times the derivative of the inside function. In the next example, I'd like to compute f prime of x. Well, when I look at that, I see, well, it's a fraction, so I probably should use the quotient rule, right? So I think that's what I'll do. And if I do the quotient rule, you take the derivative of the numerator, and you multiply times the denominator left alone. Then you do minus. Then you leave the numerator alone, and you multiply times the derivative of the denominator. And that all goes over the denominator squared, which would be 16x to the 10th. And then you just compute those derivatives, knowing what you know about derivatives of logarithms and other things. That first derivative in the numerator, you would get 0 for the derivative of 1, but then for the natural log, you'd get 1 over x cubed. Then times the derivative of x cubed is 3x squared. But then you've already got that 4x to the 5th there, so I'll just bring that down. Minus Then I've got that 1 plus natural log of x cubed left alone. And then the derivative of 4x to the 5th would be 20x to the 4th, all over 16x to the 10th. And I could certainly simplify this expression a bit if I wanted to, but I'm just going to leave it at that for now. In the last example here, we're not using x and y as our variables, but s is going to be playing the role of y, and t is going to be playing the role of x, right? So if I wanted to calculate ds dt, the derivative of s with respect to t, well, I think I will do the product rule because I'm differentiating a product of two things. The derivative of the first factor, e to the 3t, would be e to the 3t, but then times the derivative of the exponent, which would be 3. Then we've got this natural log of sine of t, which just comes along for the ride. Then we do plus. Then we leave the e to the 3t alone. And we're going to multiply times the derivative of natural log of sine of t. Well, the derivative of natural log of anything is 1 over that anything. And then we multiply times the derivative of the inside function, which is cosine. And again, we could simplify this expression a bit if we wanted to, but I think for now I'll just leave it there. As we move toward doing derivatives of more general logarithms and exponentials, we're going to have to recall some properties of logarithms and exponential functions. So first thing, just want to point out that you can have exponentials and logarithms with bases other than e. So for example, consider 2 to the x. Well, that's an exponential function with a base of 2. And if I would give that a name, say y, well, you can make a quick graph of 2 to the x, and it looks something like this. I'll put it in the upper right-hand corner here. And you can see that the graph of y equals 2 to the x is 1 to 1. It passes the horizontal line test. So this function has an inverse, and we call that inverse log base 2. And so whenever I write this equation, 2 to the x equals y, that's equivalent to the expression log base 2 of y equals x. And if you would graph the log base 2 function, it'll look something like this. The graphs are very similar to what you saw in the relationship between e to the x and natural log of x. In fact, so when you see this notation ln, that really just means log with the base of e. Another common notation is just when you see log without a base, it's understood to mean log with the base of 10. So this is usually called the natural log, and this one's called the common log. Usually on scientific calculators, you'll see a button for both the natural log and the common log. But most of the time in calculus class, we're going to be using the natural log because it's sort of the easiest one, the best one. So you get other logarithms, and they have the same kind of behaviors as, all logarithms kind of act the same. I mean, yeah, they give different numbers and, slightly different outputs, but they have the same behaviors. The important behaviors are captured in this table here. If you have any base b, then on the left-hand column here you got logarithm properties, and on the right-hand column you have the corresponding exponential properties. Like this first property here, when you take the logarithm of x times y, you can break that up as the sum of log x plus log y. And that property just corresponds to the sum of exponents rule. B to the x times b to the y equals b to the x plus y. In fact, these are really the same rule, just expressed in two different forms. One's expressed in exponential form, the other one's expressed in logarithm form. It all comes down to this equivalence that we have right here. Through that equivalence, you get the equivalence of the right-hand column and the left-hand column in this table. You have the log of the quotient, x over y. There's a little mistake there. That should be a minus. But yeah, the logarithm of the quotient, x over y, is log x minus log y. And that corresponds to the difference of exponents rules. Over here, b to the x over b to the y is b to the x minus y. The third property here, we have this nice exponent rule that says when you have log of x to the p, you can bring the p down out in front of the logarithm. And then the fourth one here is just an expression of the fact that the exponential and the logarithm functions are inverses of one another. So they undo each other. So when you do log base b of b to the x, you just end up with x. And likewise, if you do b to the log base b of x on the right-hand side, you just get x. So log base b and the exponential with base b are just undoing one another. They're inverses. And then the last property is what's called the change of base formula, or formulas. You know, if your calculator doesn't have a log base b button, then you can convert it to a natural logarithm using this formula here on the left. And if your calculator doesn't have like a 2 to the x button, you can convert it to an e to the something in that right property there. So these are all properties that you really need to know. Like everything in this table, you kind of need to have at your fingertips at all times as you're doing the problems, especially the problems in this particular section. But just moving forward, you know, you have to, logarithms come up enough that you just need to be able to deal with them algebraically as needed. So let's see how we can take advantage of some of these properties to help us compute derivatives. So in this first example, I've got y equals the natural log of this quotient. Well, before I jump in and just start differentiating, maybe I should apply some properties of logarithms to simplify. See, if I were to take the derivative of it as is, which I could do, I would have to do 1 over what is on the inside. But then when I go to take the derivative of the inside by the chain rule, I would have to use the quotient rule. And the quotient rule is kind of the yuckiest of the derivative rules because, you know, it's just the most complex. So if you can avoid using the quotient rule, that's always nice. And you can here because before you take the derivative, you can say, well, this is really natural log of x squared minus natural log of 1 plus x cubed using that the quotient log rule on the previous page. And I can even go one step further. That natural log of x squared, I can bring the exponent down. So I can write that as 2 natural log of x minus natural log of 1 plus x cubed. I can't do anything with that x cubed, but the expression that we have on hand now, here on the far right, is much easier to differentiate than the original. So now if I want to do dy dx, the derivative of the first term is just 2 over x, and the derivative of the second term is going to be 1 over 1 plus x cubed, then times the derivative of the inside function, which would be 3x squared. So I'll just write that in the numerator here, and done. That was a lot easier than having to do the quotient rule if I would have just jumped in and started doing the derivative right away. And the final answer that we have is also reduced algebraically a lot more than what we would have gotten if we had just jumped in without simplifying first. Here's another example where you can take advantage of some logarithm properties before differentiating. So the original function here is natural log sine of x times the square root of x. Well, we have that rule that says you could write that as the natural log of sine of x plus the natural log of square root of x. And then I see that, you know, that square root of x, that's really just x to the 1/2, right? So that radical is really just an exponent hiding from it in disguise. So I can bring that 1/2 down too. So I can write this as natural log of sine of x plus 1/2 natural log of x. Now I want to differentiate it after I've simplified it a bit. So dy dx now would be, okay, the derivative of the first thing is 1 over sine of x. And then you got to multiply times the derivative of the inside, which would be cosine. And so I'm just going to put that cosine in the numerator here. Plus, and then I get 1/2 times the derivative of sine of x, which is 1 over x. So I can write that as 1 over 2x, and done. If I had just jumped in and started doing the derivative of the natural log of sine of x times square root of x the way it was originally, I would have had to, you know, do 1 over the inside. Then I'd had to use the product rule to differentiate the inside, and it would have just been a little bit more complicated at the end. So this is simpler. Okay. All right, so now that we have control of these properties of logarithms and we understand that we can have logarithms and exponentials of different bases, then we want to know what are their derivatives of these two new kinds of functions that we're working with, the b to the x and the log base b of x. Well, the first formula is that when you differentiate b to the x, you get b to the x, but then times this natural log of b. B here is just a positive constant, right? So how do we get this derivative formula? It's actually remarkably simple. You just have to use the change of base formula and use what you know about e to the x. So if I want to take the derivative of b to the x, I can do the change of base formula. So that's going to be the derivative of, okay, if I change the base to e, it becomes e to the x natural log of b. So that's just applying the change of base formula that we learned on in the table on the previous slide. But we know how to differentiate e to a power. The derivative of e to a power is e to that power, and then you take the derivative of whatever the exponent is. Now, you might be looking at that and think, I'm going to do the chain rule, but you need to remember that natural log of b right here is just a constant. Like if b were equal to 2, natural log of 2 is just some number that you would get when you plug it into your calculator. So you're just differentiating a constant times x. So this is like doing the derivative of something like 2x. If you took the derivative of 2x, you'd get 2. So if you take the derivative of x times natural log of b, you're just going to get natural log of b. So you end up with that natural log of b is that derivative, and then you still have that e to the x natural log of b there. But remember, e to the x natural log of b is the same thing as b to the x. So this just ends up being natural log of b times b to the x. And that's what we were supposed to get, right? Okay, so there's one new derivative formula. And also, we can take the derivative of log base b of x, and it turns out to be just 1 over x, but then multiplied times a constant, natural log of b. So it's very similar to the rule, when you take the derivative of natural log of x, you get 1 over x, right? Without that extra constant. I mean, if you wanted to, you could write that as 1 over x times natural log of e. But what is natural log of e? That's equal to 1. So it's really an extension of our previous natural log formula. This also comes from doing change of base. If I want to take the derivative of log base b of x, that's the same as taking the derivative. Okay, if I change it to the natural log, it becomes natural log of x over natural log of b. But dividing by that natural log of b is just dividing by a constant. So I can pull it out. That's 1 over natural log of b in front. And now I'm taking the derivative of natural log of x. And we know that formula, that's 1 over x. So you get 1 over natural log of b times 1 over x, which is the same as what you got right there, right? And then we can also do this extension for the log base b of absolute value of x. Well, if I want to take the derivative of log base b of absolute value of x, I can still use the change of base formula on that, and that would just be natural log of absolute value of x over natural log of b. And just like before, I can pull the 1 over natural log of b out, and I'm taking the derivative of natural log of absolute value of x. But we learned previously that the derivative of natural log of absolute value of x is just 1 over x. So this ends up being 1 over natural log of b times 1 over x also, which is what we were hoping to get. So here you have these 3 new derivatives, really 2. And so these are some derivatives that you just need to know, and then we can use them. Good thing is they're easy to remember because they're almost the same as the derivatives for e to the x and natural log of x. You just have this extra constant of natural log of b or 1 over natural log of b to include. So like, for example, if I want to differentiate the function y equals 3 to the x squared plus sine of x, the base is 3 here. So if I want to differentiate that, the rule says it'll be natural log of 3, and then times, you just get that same exponential function, 3x squared plus sine of x and exponent. But the exponent this time is a whole function, and so you have to use the chain rule and multiply times the derivative of that inside function. And so you get natural log of 3 times 3 to the x squared plus sine of x, and then that derivative there is 2x plus cosine of x. So if you felt good about differentiating e to the x, this isn't much harder. You just have this extra little constant that you have to put in. And on the second function here, it involves differentiating the log base 2 function. But this time, I've got a product of two functions, right? So I'm going to use the product rule. But before I get into doing that, I think I might try to make life easier on myself by using a logarithm property, because here I see that what's inside that log base 2 is really x to the 5/3. And I know that logarithms have the property that you can bring the exponent down. So I could write this as 5/3 x squared log base 2 of just x. That'll be a little easier to differentiate. So now dy dx is, okay, take the derivative of the first term, which will be the 5/3 x squared. So just bring the 2 down, and you get 10/3 x. And then you still have that logarithm, log base 2x, plus, then I'm going to leave the 5/3 x squared alone. And the derivative of log base 2 of x is 1 over x times natural log of 2. Of course, you could cancel the x in the denominator with the, you got that x squared in the numerator, but I'll just leave it like that for now. By the way, you can see, like, I put the x in front of the natural log of 2. The reason we usually put the x in front of the natural log of 2 is because if you write it the other way around, like you write natural log of 2 times x, like, if you just wrote it like that, you might get confused and think that x is inside the logarithm, but it's not. So if you write it the other way, you want to be sure and use parentheses to keep things separate. Okay. So now we know how to differentiate any exponential or any logarithm, regardless of base. So that's pretty cool. Another cool little thing that we can do now that we understand exponentials a bit better is we can verify that the general power rule works. The power rule works for any exponent p. When we first introduced the power rule, we would only be able to do things like derivative of x to the 4th or something like that. Then we saw that we could do negative exponents. So we saw why, I could do something like the derivative of x to the negative 3rd using the same power rule. But we never really saw why it was true that we could do like derivative of x to the 1/2 using the general power. Like, this would just be 1/2 x to the negative 1/2 using the power rule, right? But we didn't ever see why it worked for, say, fractional exponents, or something like where the exponent's something really weird, like x to the pi would be pi x to the pi minus 1. We never saw why it was true that we could get away with doing those weird exponents. But now we can see how we can make it work for any exponent. Let me show you why it works. The trick is, in differentiating x to the p, we're going to do a change of base. I want to change it to a base that I know something about. So I'm going to change it to the base e. So I can write derivative of x to the p as being the same as taking the derivative of e to the p natural log of x. So that's the change of base formula applied to x to the p. And this is nice because I know how to differentiate e to anything. The derivative of e to the anything is just e to whatever was in the exponent. And then you multiply times the derivative of the exponent. Now remember here, p is a constant. So in doing that derivative there, I still have this e to the p times natural log of x. And then the derivative of p times natural log of x would be just p over x. And then for the grand finale, I just have to remember that e to the p natural log of x is really just the same thing as x to the p. So let me write this as x to the p times p over x. So this is p times x to the p over x to the 1, and that's the same as p times x to the p minus 1, which is what we're supposed to get for the power rule. Pretty cool, huh? That change of base formula is pretty handy. Like it. So now we feel good about differentiating something like in this next example. Okay, the exponent is a constant, a weird constant, square root of 2, but that works. That's your p, right? And so the power rule says bring the exponent down and then reduce the exponent by 1. So the exponent becomes square root of 2 minus 1. I don't really have a nice way to collapse that down to some single value, but, or, it is a single value, but I can't collapse it down to a smaller expression. That's just what it is. So there you go. So now general power rule is something that we have established. We're not taking it on faith now. There is one thing that we took on faith in this class so far, and that was that the derivative of e to the x was e to the x. Really, even what we mean by e to the x, we took it on faith that that was something that made sense itself. This is where this class gets its name, early transcendentals. We take this little shortcut to get to e to the x and natural log of x just by assuming that, e to the x makes sense and its derivative is e to the x. There's actually a sort of nicer theoretical way to establish all that, but it might feel weird to beginning students, so a lot of people go with this sort of early transcendentals way of approaching calculus. Plus the engineers like it because they can get to using natural logs and logarithms right away. The last topic for this lesson is the topic of logarithmic differentiation. So this is a really cool process actually that allows you to differentiate functions that we don't have any formulas or methods for differentiating otherwise. And it also allows you to take some things that you already know how to differentiate, but make it easier or less messy. Especially when you're dealing with expressions that involve lots of products, exponents, and fractions. So here's what logarithmic differentiation is. So you have some function, y equals f of x, and you want to differentiate it. So the first step is you just take natural log of both sides of that equation. So if you set up y equals some function, then you just do natural log of y equals natural log of that function. Now if that function f of x involved exponents, you could bring those exponents down. If there was products, you could break it up, because we have a logarithm property that the logarithm of a product is the sum of the individual logarithms. Or same thing with quotients, except you subtract. So this step right here of taking the logarithm of both sides will sort of collapse, or I guess sort of expand it out. It'll bring down exponents and get rid of radicals and things of that nature for you, which makes it simpler to differentiate. And then, so that's what you do in step 2 is you just you use what you know about logarithms to simplify the expression on the right. And then the last step is just to use implicit differentiation to figure out what your derivative is. And we already know how to do implicit differentiation, so we should be good to go. So here's a great example. You got y equals sine of x all raised to the x. At this point, you have absolutely no formula or method to calculate this derivative. It's a fairly simple looking function, but if it were an exponential function where the base is constant, but the exponent's variable, we could differentiate that. Or if it were just a power function where the base is a variable, but the exponent is a constant, we could differentiate that. But here we've got something where both the base and the exponent are variable. We don't have any rules for something like that. But we can do this logarithmic differentiation process, the first step of which is to take the natural log of both sides of that equation. The second step is to use your properties of logarithms on the right-hand side to simplify. Well, one property I know about logarithms is that I can bring exponents down. So I could write this as x times natural log of sine of x. And the third thing is to implicitly differentiate both sides with respect to x. Okay, on the left-hand side of this, we're differentiating natural log of y. But we know y isn't just the variable y. Y is this whole function at the top here. So we have to use the chain rule when we differentiate it. So we'd go, the derivative of natural log of y is 1 over y. But then we have to multiply times the derivative of the inside. On the right-hand side, it's all x's, right? There are no y's. So we just differentiate like normal on the right-hand side. And I would use the product rule and write that as, well, derivative of x is 1 times natural log of sine of x, plus, then we leave the x alone, and the derivative of natural log of sine of x would be 1 over sine of x, then times the derivative of the inside function, which is cosine, so I'm just going to put that in the numerator there. And then for the grand finale, I'll just solve for y prime. Y prime, multiply both sides by y, and you would get y times all that stuff on the left-hand side, which I could write as x times cotangent there. And then just remember what y is equal to. At the very beginning, we knew y is equal to sine of x times x, so I can put everything back in terms of the variable x by substituting sine of x raised to the x in place of y there. And there is your derivative. So we just did something pretty cool. We differentiated a whole different kind of function that we had no way no formulas for anything. So this logarithmic differentiation is a pretty cool process. So not only does it allow you to calculate derivatives of new kinds of functions, but it allows you to calculate derivatives of functions that you knew how to calculate the derivative of, but it would have been extremely yucky. Like here's an example that, based on information that you knew even before you learned about logarithmic differentiation, you could have differentiated this. You could do the quotient rule, and then in the numerator, you got to use the product rule, and then there's some exponents, so you got to use the chain rule a bunch. And if you differentiate this the old-fashioned way, it'll just be a bit messy. You can do it. It's just messy. But the logarithmic differentiation process actually simplifies it. So if I would take natural log of both sides and then take advantage of logarithm properties, I'll make this a lot simpler. Okay, on the right-hand side there, I'm doing the logarithm of a fraction, so I can do logarithm of the numerator minus logarithm of the denominator. And also, I'm doing logarithm of a product there, so I could write that as the logarithm of the first term plus the logarithm of that second term. Now that last term there, we're doing natural log of e to the tangent x. Natural log and e to the power are inverses of one another, so that just collapses down the tangent of x there. We can do more simplification because I've got exponents that I can pull down. I can pull down that 5, and also that square root's really an exponent of 1/2, so I can pull a 1/2 out there. Well, that's about as good as we can do with simplifying things using the properties of logarithms. So now I'm at the point where I want to implicitly differentiate. So I'm going to differentiate both sides with respect to x. On the left-hand side, just like before, you get 1 over y times y prime. On the right-hand side, the derivative of the first term would be 5 times 1 over 2x plus 6, and then times the derivative of the inside function is 2. Then on the second term, I'd get 1/2 times 1 over what's on the inside of that middle one. So 1 over 1 plus sine squared x. But then we got to take the derivative of that inside function. Just for a second, I'll just leave that as sine squared of x prime. Then I still got that tangent of x there. Oh, I got to take the derivative of the tangent, and that's secant squared. The only derivative that we haven't computed so far is this sine squared of x prime. To do that one, let me just find a little place to do an aside here. If you're doing sine squared of x prime, that's really sine of x squared prime. So if you're taking a whole function squared and you want to differentiate it, you can bring the 2 down. Then it becomes sine of x to the 1 times the derivative of the inside function is cosine. So you get 2 times sine times cosine there. So going back to my problem, I'm going to solve for y prime by multiplying both sides by y. And then I'm going to remember what y is equal to times. And then I have all this stuff. Looks like I'd have, if I simplified a little bit, I'd have 5 over x plus 3 by canceling off the 2. And then on the next term, I'm going to have sine x cosine x over 1 plus sine squared of x. Again, I had a 2 and a 1/2 cancel. See, because I was putting this 2 times sine x cosine x here, and then the 2 and the 1/2 canceled. And then I got that secant squared of x, and then that's your answer. All that. And this term here in black was the y. Whenever I multiplied both sides by y, I just got what y was from the very beginning. Y equals all that mess, and so I just substituted it in. So I'm the first to admit that this problem was a little bit on the yucky side in terms of how much algebra you had to do to get at it. But when you look at, and really, in practice, I could have gone straight from this first step to this simplification right here. Because, mentally I would have said, okay, I'm going to do natural log of the top minus natural log of the bottom, and then the top one's a product, so it'd be natural log of that first factor in the top plus, and I would say, I'll bring that 5 down. I could have jumped straight to that if I know my logarithm properties well. And then the point, though, is that by the time you get it simplified there, all those individual derivatives are much simpler than what you would have had at the beginning. Now, the expression that you get at the end is kind of yucky. There's no getting around that. But getting to it wasn't that hard. We just had to exercise good bookkeeping as we went so that we don't make some sort of algebraic mistake or, miss a sign or something like that. Okay. I think we'll stop there. I just want to take a second to reflect on all the stuff that we learned today. We learned how to take the derivative of anything, any base, b to the x. We learned how to take the derivative of any logarithm base b. And we learned logarithmic differentiation. Those were the big things we learned today. We had to sort of review some properties of logarithms to help us out along the way. But this was the big stuff here that you learned, that you'll be needing to carry forward with you. Okay, stop there, and I'll see you next time. Bye.